In this video, we will complete the implementation of our neural network library. The main algorithm that we need to implement is backpropagation. Without further ado, let's get straight in. In the math video, we discussed how, at the end of the model forward pass, we have a loss function to calculate how wrong the model's predictions are compared to the expected output. We're going to first implement these loss functions. To kickstart backpropagation, we need to find the derivative of this error with respect to the model's predictions. You might also remember me mentioning that in the implementation, we will directly calculate the gradients to reduce the computations. Here, we're going to implement these three loss functions: the mean squared error, the log loss function, and the categorical cross-entropy loss function. For our convenience, I have already implemented these before, because they're just simple formulas and deriving them would require a separate video by itself. So if we quickly go through these functions, the mean squared error, which is what we would normally use for regression tasks, takes the predicted and the expected NumPy arrays, finds the shape of the predicted output, which would be the number of examples, and then it would find the difference between the predicted and expected values, multiplied by 2 and divided by n. What this is doing is averaging out the individual errors between the predictions. The log loss and categorical cross-entropy loss functions, on the other hand, are meant for classification tasks. The log loss function is often used when we have a classification task with two output labels, and the categorical cross-entropy loss is used for classification tasks with more than two labels. Here too, you can observe that we're using the clip function to clip the output values to be slightly greater than 0 and slightly less than 1. And the reason being that here we're dividing the expected values by the predicted values, and if any value that is predicted is equal to 0, then we would get a division by 0 error. So those are the loss functions that we'll be using in our neural network library. Now let's move on to the activation functions. In the previous video, we implemented these call methods for ReLU, sigmoid, and softmax activation functions. Now we're going to implement this derivative method. What the derivative method is going to do is it will take the gradients calculated up to the next layer and calculate the gradients with respect to the activation function for the current layer. Since the activation function changes the pre-activated output of the layer into an activated output, we need to find the rate at which this change is affecting the error, and that is why we need these derivative methods. Now, if you recall from the previous video, whenever the ReLU input is less than 0, the output will be equal to 0, and if it's greater than 0, it will be equal to the output itself. We also discussed that this means that ReLU is a combination of a horizontal line and the line y equal to x. So if we find the derivative, we're going to have to return these values. So we're going to use the np.where function, and we're going to check where the output is less than 0, less than equal to 0, and return 0, and otherwise we're going to return 1. We're going to multiply this with the gradient so far. What this is doing is it's checking if the output, maybe we should rename this to be pre-activated output. So if the pre-activated output is less than or equal to 0, then ReLU would output 0 as its activated value. So the gradient at that point would be equal to 0. Similarly, if the pre-activated output is greater than 0, then the output would just be the pre-activated output, which would lie on the line y equal to x. The slope of the line y equal to x is simply 1, which is why we're going to return 1 here as the derivative. And if we remember from backpropagation, that is simply multiplying the gradients that we've calculated so far, that is reusing those gradient values and multiplying it with the current derivative because of the chain rule. So this is how we would implement the derivative method for the ReLU class. Moving on to sigmoid, I'm going to make the same change here. I'm going to update output to be pre-activated output. And even here for softmax, we'll change output to be pre-activated output. Now, for sigmoid, let's not get too deep into the math, but the derivative is simply going to be this value that we've calculated here times 1 minus the same value. Now, if you've taken a calculus class before, then you would be able to derive the derivative of 1 over 1 plus e to the negative x, and you would recognize that you would get this expression here. And let's not forget, we need to multiply that result by the gradients calculated so far. Finally, we have to implement the softmax derivative method. Now, since softmax acts on each row in the pre-activated output matrix and not just each value in the matrix, we have to do some more math here. I'm not going to go too deep into this because it involves vector calculus. So let's just say that this is how we find the derivative of the softmax function. We first run the pre-activated output through the softmax layer once again in order to calculate the activated output. Then we get the batch size and the number of classes, which are the rows and columns of the output matrix. Then we have to calculate this Jacobian matrix. And then for each example in the batch size, we have to create a couple of more matrices. And then we can do some linear algebra to find the derivatives up to the softmax layer. Now that we have implemented the gradient calculations for the output of the model and for each activation function, we can implement backpropagation for a single layer. We're going to do that in this back method in the layer class. So once again, the back method just works in reverse of the call method. So we're first going to check if there is any activation function. If there is an activation function, we're simply going to call the activation function's derivative method that we defined just now in the activations file. The derivative method expects the pre-activated output and the gradients calculated so far, which would be in the ret variable. And this would be our new gradients calculation. Then we have to find the update matrix, which would just be the current inputs matrix multiplied with the ret variable. Then we have to find the return value from this function, which would be this variable new ret, and this will simply be ret matrix multiplied with self.weights. Now finally, we have to account for the bias in the layer. If there is a bias term, new ret will be equal to all the rows and all but the last column, because the last column contains all the bias terms. Then we return the new ret value to be propagated backwards to the previous layer. Now, if you notice here, we need to use the current inputs to the layer, the pre-activated output, and we need a variable called the update matrix. So we're going to initialize these values to be none in the constructor of the layer class. So self.update matrix is equal to none, self.current inputs equal to none, and self.pre-activated output equal to none. Next, when we're doing the forward pass through the layer, we're going to store the current inputs to the layer in the current inputs attribute by copying it. The reason we need to copy the layer inputs is because if we simply set them to be equal, this is going to equate the references. That is, any modifications to layer inputs would also modify current inputs, but we do not want that to happen. So we have to copy the value over to the current inputs attribute. Next, if there's also the activation function, then we'll copy over the pre-activated outputs. Layer output. This way, we can use these variables in the back method of the layer class. And this would have to be self.preactivated output. Finally, after backpropagation is completed in all the layers of the model, we'll have to update the weights, and we do that as follows. Self.weights minus equals self.alpha times self.update matrix. This is, as you recall from the math video, how we update the weights. We scale the update matrix by the learning rate to ensure that we don't miss the minimum during the optimization process. And we also reset all of these values that we initialized here back to none for the next pass through the neural network. That, in a sense, is backpropagation through a single layer of the model. Now we have to implement backpropagation for the entire model. We're going to do that in the layer list class by writing its own back and its own step methods. What the back method will do is for each layer in self.model in reverse, this syntax ensures that we're iterating through the model in reverse, which is how we would do backpropagation. We're going to call the back method and pass in the gradients calculated so far, which will be this error variable. And then we'll store the return value back in the error variable to be propagated on to the previous layer. And finally, to update the weights in every single layer, we're going to iterate through all the layers once again in the model and call the layer.update function. This will update the weights and biases in all the layers of the model. And with that, we have implemented the forward pass through the neural network and the backward pass. We're just going to add a couple more methods to the layer list class, which would allow the user to train the model without having to combine all these functions by themselves. First, we're going to write this method called fit. What fit does is it will implement the training loop of the model. It's going to take a bunch of training data, the expected values. It will pass the training data through the model epochs number of times, and epochs just means how many times the input data will be seen by the model, and we're going to train the model. We'll take a couple more parameters, alpha and batch size. Alpha will be the initial alpha value, the initial learning rate of the model, and batch size will indicate the size of the batches we wish to use during our training. We'll also take this parameter, loss deriv function, which is going to be one of these loss functions that we defined in the loss file. That will allow us to calculate the derivatives to kickstart the backpropagation. We're going to start off by writing an outer loop to iterate as many times as epochs. So the contents of this loop will run as many times as epochs. And in each epoch, we need to feed the entire input data into the model. First, we're going to create batches of the input data by calling this batch static method that we've defined up here. That would look as follows. We'd get batched input, batched expected is equal to layer list dot batch input data expected batch size. Next, for I in range len batched input, that is for each input batch in our batched input variable, we're going to pass this in to our model and we're going to get the predictions. This will be model output is equal to self batched input. This is going to pass the batched input into the model and return the model output by calling the call method. Then we're going to call self.back to backpropagate the error. The initial error will be calculated by calling the loss deriv function. And to that, we have to pass the model output or the model's predictions and the expected values, which we can do as follows. After we've calculated the derivatives in all the layers of the model, we have to call the step method to update the weights and biases in the model. Now, before we start the training loop, we want to call the alpha update, which was the set alpha method, to set the initial learning rate in all the layers of our model as follows. And we're going to periodically update this alpha value. So I'm going to say prev update is equal to 1. And here, instead of just having an underscore, let's say for e in range epochs, we're going to run through this training loop. And if e is 10 times the previous update, then we're going to set the alpha value to be a new alpha value. And we'll calculate this new alpha value by dividing the previous value by 10. We should also update the previous update variable to be this new point. That, in a sense, is our training loop. Now we have to implement this batch static method, which we're going to do as follows. We're going to get num data is equal to input data dot shape. This way we're going to get the number of examples in the input data. Next, we're going to store the indices of all of these data points as follows. I in range num data. Then we're going to shuffle these indices because we want to pass the data points into the model in a random order. To randomize the values in the indices list, we're going to call the shuffle function. The shuffle function is defined in the random library, which we'll import as follows. After we've shuffled all the indices, we're going to create two lists, batched inputs, batched expected, and we're going to return these values at the end of the function. These two lists are going to contain the batched input data and the batched expected values. Let's also just convert these into NumPy arrays. And add a return statement here. To populate these two lists, we're going to iterate in num data divided by batch size. What this is doing is determining the number of elements that will be in the batched inputs and batched expected lists. Let's say, for example, batch size is 32 and the number of data points we have is 64. Then we're going to have just two batches of size 32, which is 64 divided by 32. And that's what this is ensuring. If the number of data points was 65, even then we would only be able to create two batches of size 32, which is why we're using the floor division operator. So in each batch, we're going to define a batch int, comma batch x, and these are also going to be two lists. Then let's just change this to I, and then for j in range batch size, this will allow us to collect batch size number of input data points in the batch input and batch expected lists. We're going to append batch inp.append input data at the index indices batch size times I plus j. What this is doing is it's calculating the current index that we want to add, which would be batch size times I plus j. Then we're going to get that index from the indices list, and we're going to get the input data point corresponding to that index using this syntax. Similarly, we're going to append to the batch exp list the same value from expected. After we have populated batch inp and batch exp with batch size data points, we're going to append batch inp and batch exp to the batched inputs and batched expected lists. So batched inputs dot append np dot array batch inp and batched expected batch exp. This is how we're going to batch our data points and then pass the batches into our model for training. Finally, after our training is done, we want to implement a predict method, which given a set of inputs will return the model predictions. This would be our training dataset or our inference dataset. So after our model is trained and we want to test it out on other data that it's not been trained on, we will call the predict function. Here, we're going to create a list called predictions, which will store the predictions of the model for each input. Then we will iterate through each input in the inputs argument provided, and we will append to predictions the result of passing that input into the model. And that would look as follows. Self inp. We will then return the predictions of the model as follows. One final thing that we have to keep in mind is that since we're using batching in our neural network, we need to ensure that this inp that we pass in the model in the predict method has a shape equal to 1 comma num features. But if we use this syntax, then this 1 will be missing and we're going to get a cannot matrix multiply error. To resolve that, we're going to use this function called expand dims. And the expand dims takes a numpy array, the dimension in which to expand the array. Here, the axis would be 0 because it's the first dimension that we want to increase. And that is it. That is the entire layer list class and layer class in this file, the activation functions, and the loss functions. Now, as promised, let's put all of this together and build a handwritten digits classifier in main.py. In order to save time, I've put the code together up here for us to follow through. First, we're going to import NumPy and Matplotlib for calculations and graphing. Then we're going to import all the classes that we wrote in the activations, the loss, and the layer files. And then from sklearn, we're going to import the datasets. We're going to then load the mnist digits dataset using this syntax here and extract the images and labels. Then we're going to use the built-in train test split function to split the images and labels into training and testing data points. We're also going to reshape the training and testing images because each image is an 8 by 8 matrix, and our model will take only a one-dimensional matrix. So we're going to reshape this to be a 1 by 64 matrix. Next, we're going to convert each of the labels into arrays of probabilities. Since this is a classification task, we want to make sure that the expected values are arrays of probabilities. We're going to do that using this syntax here. We're iterating through all the expected labels in the training dataset. We're creating a list of size 10 with each value initialized to 0, and we're going to update the probability of the label to be 1. This is going to convert each label. Let's say the label is 2 into lists as follows. and the value that is 1, its index will indicate the label. We're going to convert these lists of probabilities into a NumPy array and reshape it to match the final layer of our neural network. Before we go through these two functions here, let's just go through how we write our neural network. We're first going to scale the input data to avoid exploding gradients. That is, if the values in our testing and training dataset are greater than 1, then there is a chance that during the matrix multiplication, the gradients get stuck in a vicious cycle where they exponentially grow and result in an unusable model. We'll also define these hyperparameters here, the learning rate and the batch size, and we'll write our classifier as follows. So it will be a layer list object with 2 layers. The first layer will have 64 inputs and 28 outputs, and the second layer will have 28 inputs and 10 outputs. These 10 outputs represent the 10 labels for the 10 digits. Additionally, since it is a classification task, we're going to use the softmax activation function in the last layer. To train the model, we're going to use the fit method. We're going to pass in the reshaped training dataset, the reshaped expected values, the number of iterations, or the number of times we want the input data to be seen by the model, the alpha value, the batch size, and the loss function. We're going to use categorical cross-entropy loss here because there are more than 2 labels that we can classify into. After the training, we're going to evaluate the model using the classifier.predict method. We're going to pass in the testing dataset, and we're going to convert the results of the model into a list of labels using this convert function. The convert function takes in the classifier predictions, which would be a list of probabilities. Then it will find the index of the largest probability as follows, and it will append that index into predictions because that's the label that the model is predicting. Finally, we're going to pass all of that into this display images function, which is just a nice helper function to display the images and the model predictions for us to visually evaluate. Let's try running this and confirming that the library works as we expect. So it should be activation func and not activation. That's the keyword argument. Let's try running it again. Okay, I found the reason why it's happening. It's because here we didn't pass in the index here. So we were passing in the entire batched input matrix and not each batch in the batched input matrix. Let's try again. Oh, oops, that is again another tiny mistake. We can't multiply the current inputs with the ret. We have to, in fact, transpose it. That is, we need to switch the rows and columns of the matrix to ensure that the shapes match. I would recommend you to draw out the current inputs and the ret matrices and see why the shapes don't match if we don't take the transpose of the current inputs. And similarly here, we need to take the transpose of this weight matrix. And there we go. That's our model's performance on the testing dataset. As you can see here, the first value is the model prediction and the second value is the expected label for each of these digits. And we can see that the model is done pretty well overall. There are a couple of issues, like here it's predicting this 1 is a 9. Here as well it's predicting this 1 to be a 9, as well as here. And here it's mistaking this 1 to be a 3. Oh, and here it's mistaking this 8 to be a 5. But overall, if we go through this, it looks like most of the digits have been classified correctly. We could, of course, tune some of these hyperparameters, add a few more layers and different activation functions to try and improve the model, but that's up to you. Do feel free to play around, add more layers, try different activation functions, a few activation functions that you write by yourself, and see if you can get your model to perform better. You could also use this model on other data sets that are available. You could also try this in some regression tasks where you have a bunch of input data points with a certain relationship that you try to predict using a neural network. The possibilities are just endless. With that, we've finished the implementation of our bare bones neural networking library in Python using only the NumPy library. Feel free to comment if any part of the code is unclear to you or the math is unclear, and I will do my best to help you understand. See you all in the next series.